In 1950, at a lunch table in Los Alamos, New Mexico, Enrico Fermi put down his fork and asked a question that no one has been able to answer in the 75 years since. Where is everybody? He had been doing mental calculations during the walk to the cafeteria. Fermi was one of the greatest intuitive calculators that ever existed. The kind of mind capable of estimating the force of a nuclear explosion by tossing bits of torn paper into the path of the shockwave and seeing how far they flew. And the calculations he did while walking said that something was deeply wrong. The Milky Way has around 400 billion stars. Billions of them are older than our sun by 5, 6, even 8 billion years. Rocky planets in zones where water can exist in liquid form are not rare. They're everywhere. The chemistry of life is spread throughout the galaxy like dust. Every factor we can measure points to the same place. The galaxy should be teeming with intelligent civilizations. Signals should be flooding every frequency. Probes should have visited every star system, including ours, millions of years ago. Math says we should be surrounded. But when we turn our telescopes outward and listen, what we get is nothing. Absolute silence. Something in our assumptions is catastrophically wrong. And every attempt to find out what it is leads us somewhere we don't want to go. The scale of the problem starts with the galaxy itself. 400 billion stars spread across a disk, 100,000 light years wide. If someone started counting those stars at a rate of 1 per second, they would have started before the invention of agriculture and still wouldn't be finished today. Our sun formed about 4.6 billion years ago. That sounds old, but on the time scale of the galaxy, that makes us newcomers. The oldest stars in the Milky Way have been burning for more than 13 billion years. Whatever happened on Earth, the process of planet formation and biological evolution could have started around other stars billions of years before our solar system existed. Billions of years is not just a margin. It's an almost incomprehensible head start. Life on Earth went from single-celled organisms to a species capable of splitting the atom in about 4 billion years. Could a civilization that started around an older star, even evolving at the same slow pace as life on Earth, have reached technological maturity before the first microbe appeared in our oceans? Before. That word is the whole thing. Inhabitable planets are not rare. The Kepler Space Telescope, which observed more than 150,000 stars between 2009 and 2018, found that about 1 in every 5 sun-like stars has at least one rocky planet, in the zone where water can remain liquid. Applying this proportion to the entire Milky Way, we arrive at something around 11 billion potentially habitable worlds, Earth-sized, just in our galaxy, including planets that orbit around red dwarf stars, which are much more numerous than stars like the Sun. The number rises to tens of billions. And the ingredients for life aren't limited to Earth either. Astronomers have detected complex organic molecules in gas clouds between the stars, in the tails of comets, and in meteorites that have fallen to the ground on our planet. Amino acids form naturally in space. Water is one of the most common molecules in the entire universe. The chemical components necessary for biology are scattered throughout the galaxy like seeds thrown into an open field. That's the basis of the paradox. The galaxy is old. Habitable planets are abundant. The chemistry of life is commonplace. The available time is immense. And yet, we don't see anything. Leaving radio signals entirely aside, what remains is pure physical expansion. In 1980, the physicist Frank Tipton showed something unsettling. A civilization doesn't need faster-than-light travel or any exotic technology to colonize the entire galaxy. It only needs self-replicating probes. A single robotic ship travels to a nearby star at 1/10 the speed of light. When it arrives, it uses the resources it finds there, asteroids, comets, dust, to build copies of itself. These copies set out toward other star systems. The process repeats itself. Exponential growth applied to the distances between the stars. And the math is frighteningly simple. Even taking into account travel time and construction delays, a single wave of self-replicating probes could visit every star system in the Milky Way in something like 1 to 10 million years. That sounds like a long time. On the scale of the galaxy, it's the blink of an eye. The galaxy has existed for more than 13 billion years. 10 million years represent less than 1/100th of 1% of that history. It took me a while to really let that number sink in, because the implication is brutal. If a single civilization at any point in the galaxy, at any moment in those 13 billion years, had launched self-replicating probes, those probes would have already reached every star by now, including ours. Once. Just one was enough. Just once. In the entire history of the galaxy. And the skies should bear the mark of that. The search for that mark has been thorough, and the result is always the same. Frank Drake conducted the first deliberate search in 1960, pointing a radio telescope at 2 nearby stars and listening. Silence. Throughout the 1970s, a radio telescope in the state of Ohio, nicknamed Big Ear, scanned the sky night after night. On August 15, 1977, it recorded a narrowband signal so strong that one of the astronomers on the team circled the printed result and scribbled a single word in the margin. Wow. The signal lasted 72 seconds. It came from the direction of the constellation Sagittarius. It had all the characteristics of an artificial transmission. For a brief moment, it seemed like contact. But the signal was never detected again. Hundreds of subsequent observations of the same patch of sky found nothing. Without repetition, no one was able to confirm its origin. It remains the most provocative detection in the history of the search for extraterrestrial intelligence, and at the same time, one of its greatest frustrations. The most ambitious modern effort is a program called Breakthrough Listen, launched in 2015 with $100 million in funding. Using some of the largest radio telescopes in the world to scan the nearest million stars, the entire plane of the galaxy, and the 100 galaxies closest to ours. By 2025, it has already examined millions of star systems. The result is silence. In 2020, Australian astronomers published the most comprehensive radio survey of its kind ever conducted, observing more than 10 million stellar sources. Zero detections. In 2015, another survey examined about 100,000 galaxies, looking for heat signatures compatible with large civilizations, enough to harvest the energy of entire stars through gigantic structures, the so-called Dyson spheres. Nothing. The Gaia probe mapped the position and movement of almost 2 billion stars. No anomaly suggesting large-scale engineering. Stars. Gaia mapped stars. In it, probe.
Even our own solar system has already been searched for
Artifacts that self-replicating probes could have left behind. On the moon, on asteroids, in gravitationally stable points, where an object could remain stationary for ages. The surface of the moon preserves a record that extends for billions of years. That record doesn't show any sign. In July 2025, something crossed our solar system coming from outside. The third interstellar object ever confirmed in history. A chunk of ice in dust that astronomers named Atlas. Only the third object that we are sure came from beyond the gravitational influence of our sun. Breakthrough Listen immediately turned the telescopes in its direction, looking for any artificial signal. They found nothing. No transmission, no beacon, no whisper, just ice and dust falling through the void, on a trajectory that will take it back into the space between the stars, never having been noticed by whoever might have sent it. The silence is not limited to our immediate neighborhood. It extends as far as our instruments can reach. And with each passing year, with every new telescope, every expanded survey, every interstellar visitor examined and deemed purely natural, the silence only grows deeper. So the question becomes sharper. If the galaxy has had more than enough time, more than enough planets, more than enough chemistry, and more than enough opportunity for intelligent life to arise and spread, why is it empty? Why? Because after 75 years of searching, with increasingly sensitive instruments across multiple wavelengths, we find nothing. The possible answers are not all the same. Some are hopeful. If life itself is extraordinarily rare, then the silence means that we are special, a cosmic anomaly in an empty galaxy. And our existence is precious beyond measure. But other answers are much less comforting. If life is common and intelligence is attainable, then the silence suggests something darker. That civilizations fail regularly, that they run into barriers they can't overcome, that intelligence itself carries within it the seeds of its own destruction. In 1998, an economist named Robin Hanson gave a name to this idea. He called it the Great Filter. Somewhere between the formation of a habitable planet and the emergence of a civilization spread across the galaxy, there is at least one step that is almost impossibly difficult. A barrier so unlikely, so lethal, that almost nothing gets through it. The Great Filter explains the silence by proposing that the path from dead rock to interstellar civilization contains a bottleneck so severe that it wipes out almost every species that tries to pass through. And here is the question that decides whether this idea is a reason for hope or for fear. It's a simple question. Where is the filter? If it's behind us, in an ancient step like the origin of life, then we've already passed the hardest test. We are rare. We are fortunate. The galaxy is empty because the odds never fell the right way for anyone else. But if the filter is ahead of us, at a step we haven't reached yet, then the silence isn't just a curiosity, it's a warning. It means that civilizations like ours, civilizations that build radio telescopes and split atoms and ask the Fermi question, regularly fail to survive what comes next. Something destroys them. Something so reliable and so complete that over billions of years and billions of attempts, almost nothing gets through. The galaxy has been running this experiment for 13 billion years. The expected result was a cosmos buzzing with intelligence. The observed result is total silence. And the distance between these two outcomes is the most disturbing gap in all of science. Because something is filtering intelligence out of the galaxy. Something is keeping the night sky silent. And we still don't know if that thing has already tried to stop us or if it's still waiting. The easy answers fall first. They always fall. When the silence is this absolute, the comfortable explanations are the first to collapse under their own weight. Maybe they're out there, but choosing not to make contact. The zoo hypothesis, proposed by the astronomer John Ball in 1973, suggests that advanced civilizations are already aware of Earth's existence. They have detected us. They might be watching us right at this very moment, but they made a deliberate choice not to interfere. Just like a wildlife researcher observes animals through binoculars without revealing himself. The idea has elegance. It mirrors something that humans themselves do. We create nature reserves. We debate the ethics of contacting isolated peoples. A civilization millions of years ahead of ours could apply similar principles to a species that still debates climate policy and posts pictures of their own meals on the internet. But the zoo hypothesis has a fatal weakness. For it to explain the total silence we observe, every civilization in the galaxy would have to independently reach the same decision. Not the majority, each one. Over billions of years, and maybe thousands of intelligences that evolved separately, no species, no faction within a species, no individual with access to a transmitter ever broke the quarantine. And here I have to confess that I disagree with part of how this hypothesis is usually presented. It is presented as serene, almost gentle. But human civilization can't reach a consensus between nations on a single planet. The idea that thousands of alien civilizations, separated by immense distances and operating under completely different evolutionary pressures, would unanimously agree on a single rule of behavior and maintain it for ages without a single exception, stretches credibility beyond the breaking point. All it takes is a defector, a civilization that decides to transmit, or a probe that enters our solar system by accident. Over billions of years, the probability of universal and perfect obedience approaches zero. Maybe the galaxy is simply too big, space is vast, signals weaken with the square of the distance. Even light, the fastest thing in the universe, takes 100,000 years to cross the Milky Way. Maybe no one can reach anyone. That sounds intuitive and is almost certainly wrong as a complete explanation. Distance is a barrier to conversation, but it's not a barrier to expansion over deep time. Even a slow expansion at a fraction of the speed of light fills the galaxy in a few million years. The galaxy has had time for this process to be completed more than 1,000 times. The distance makes real-time conversation impractical. It doesn't make colonization impossible. Maybe advanced civilizations turn inward. Maybe they develop virtual realities so immersive that the physical exploration of the cosmos loses all appeal. Why cross the void between the stars when you can build infinite worlds inside a computer? That's truly a fascinating possibility, but it also requires universality. Each civilization would have to make that choice independently. No species in the entire history of the galaxy deciding to remain physically active. Even if 99 turned inward, the remaining one would have already filled the galaxy many times over. Expansionist civilizations, by definition, are precisely the ones that leave evidence. Maybe they communicate using methods we can't detect. Gravitational waves, neutrino beams, quantum protocols, technologies we haven't even discovered yet. The galaxy could be buzzing with alien conversations on channels we don't have the instruments to tune into. But even if advanced civilizations migrate to exotic methods, the transition period during which they use ordinary electromagnetic radiation, which can last for centuries, should leave traces. A galaxy full of civilizations at various stages of development should include some still in the radio phase. The absence of even primitive signals from civilizations in transition demands an explanation. Each of these ideas captures something plausible. None of them, either alone or in combination, solves the paradox as long as the expected number of civilizations remains even minimally high. And with 400 billion stars, billions of years of head start, and tens of billions of habitable worlds, even the most aggressive combination of partial explanations still predicts that something should be visible somewhere. The silence isn't just quiet, it is absolute. That's what pushes the investigation back to the great filter. If the easy answers don't work, the hard answer needs to be considered. Something prevents civilizations from reaching the point of leaving a lasting mark on the galaxy. Something wipes them out. The question is, where? The starting point is the very beginning of everything. Abiogenesis, the moment when chemistry turned into biology, when molecules stopped just reacting and started copying themselves. Life appeared on Earth relatively quickly, within a few 100 million years after the surface cooled enough for liquid water to remain. Some scientists interpret this as proof that abiogenesis is easy, but we have a sample size of 1. Life on Earth arose only once. Every living organism on this planet, from bacteria to the blue whale, shares the same genetic code, the same amino acids, the same core biochemistry. If life arose easily, you would expect it to have arisen independently several times. We don't observe that. And despite decades of effort, no laboratory has produced a cell capable of replicating itself from scratch. The gap between amino acids in a flask and a functional living cell remains enormous. It's possible that abiogenesis is the great filter, that the transition from complex chemistry to a living system is so fantastically unlikely that it has only happened a handful of times in the entire history of the galaxy. If that's true, the galaxy could be full of planets that have oceans, atmospheres, and rich organic chemistry, but no life. In that scenario, Earth is a winner of the cosmic lottery, and the silence is the sound of a universe where the first step is almost impossible. If that's the case, the hardest part is already behind us. But the story doesn't stop there. Life appeared on Earth 4 billion years ago. For the next 2 billion years, all life consisted of single-celled organisms, bacteria and archaea. Microscopic, simple, successful, but fundamentally limited. Then, somewhere between 1.5 and 2 billion years ago, something extraordinary happened. A single-celled organism swallowed a bacterium. Instead of digesting it, the host cell kept the bacterium alive. Over time, the swallowed bacterium became the mitochondrion, the structure that provides energy for every complex cell on Earth. This event, endosymbiosis, gave rise to cells with a nucleus. Every animal, every plant, every fungus on this planet descends from that single fusion. In 2 billion years of microbial life, with trillions of interactions between cells happening every day, this specific fusion happened exactly once. The British biochemist Nick Lane argued that the energy constraints on simple cells make complexity almost impossible without the specific energy boost that the mitochondria provide. And acquiring mitochondria required an unlikely accident. If Lane is right, most planets with life may be permanently stuck at the microbial stage. Oceans teeming with bacteria, no path to complexity, no animals, no plants, no brains. The universe could be full of living worlds that look as dead as Mars from a distance, because their life never made the leap. And the story goes even further. Complex cells appeared. Multicellular organisms came next. Animals diversified. Over the past 540 million years, hundreds of millions of distinct species have evolved on Earth. Trilobites dominated the seas for almost 300 million years. Dinosaurs reigned over the land for more than 160 million years. Insects have thrived for 400 million years. Of all these hundreds of millions of species, throughout all that time, exactly one developed technological intelligence. One. The paleontologist Stephen Jay Gould argued that if it were possible to rewind the tape of evolution and play it again, intelligence might never reappear. It is not inevitable. It is contingent. A statistical accident. Most successful organisms never need it. Sharks have survived for 450 million years without ever having a single thought about radio telescopes. Each of these transitions could be the filter. The origin of life, the origin of complex cells, the origin of intelligence. Each one could be the bottleneck. And if any of them is the main filter, the implication is hopeful. The hardest step is behind us. We've already gone through the eye of the needle. The galaxy is silent because almost nothing else has come this far. But there is another possibility, and it's the one that changes everything. What if the filter isn't behind us? What if it's ahead, the timeline of human technology? For about 300,000 years, anatomically modern humans existed without producing anything that could be detected from another star system. And then, in an astonishingly compressed burst, everything changed. Agriculture, 10,000 years ago. Writing, 5,000 years ago. The scientific revolution, 400 years ago. The Industrial Revolution, 250 years ago. We split the atom 80 years ago. We landed on the moon 56 years ago. We built artificial intelligence capable of human-like reasoning less than 10 years ago. From stone tools to nuclear weapons in a cosmic instant. And here's the detail that makes this instant so dangerous. The same acceleration that made us detectable also made us capable of destroying ourselves. We developed the ability to transmit radio signals into space and the ability to annihilate civilization with nuclear weapons within the same decade. Visibility and self-destruction arrived together, hand in hand. The historical record contains moments when the survival of civilization depended on the judgment of a single individual operating under extreme pressure with imperfect information. In 1983, Soviet officer Stanislav Petrov chose not to report what appeared to be 5 American nuclear missiles heading toward the Soviet Union, detected by early warning satellite. His judgment that it was a false alarm was correct. In October 1962, aboard a Soviet submarine near Cuba, unable to communicate with Moscow, 2 out of 3 senior officers voted to launch a nuclear torpedo against American ships. The third, Vasily Arkhipov, refused. A single dissenting vote on a submarine isolated from the outside world prevented what could have been the opening act of a thermonuclear war. In 1995, a Norwegian research rocket triggered the Russian nuclear alert protocols. President Boris Yeltsin had minutes to decide whether or not to order a retaliatory strike. He chose to wait. Every time, survival depended not on the robustness of the systems, but on the human judgment of a single person. That's not a formula for long-term reliability. Stretched over time, in the long run, the math becomes relentless. A civilization facing a 2% chance of self-destruction per century, those odds seem manageable. 98% chance of survival per century, but that probability accumulates. After 1,000 years, the accumulated chance of survival drops to about 82%. After 5,000 years, 36%. After 10,000 years, 13%. After 50,000 years, less than 1%. A civilization would need to survive for millions of years to leave the kind of lasting presence that would solve the Fermi paradox. At 2% per century, the chance of lasting 1,000,000 years rounds down to 0. That's the coldest framing of the Great Filter. It doesn't require a single dramatic catastrophe. It doesn't need an asteroid or a superweapon. It only requires that technological civilizations are intrinsically unstable over long periods of time. That the tools they build to grow are the same tools capable of destroying them. That the margin between thriving and collapsing remains permanently thin. That over enough centuries, something always ends up going wrong. Not because the universe is hostile, but because intelligence is powerful. And power tempered by sensitivity and perfect wisdom, sustained over geological time, without a single fatal mistake, may be a condition that nothing in the universe has ever achieved.
And there's a version of this argument that is worse than self-destruction. Because destruction, at least, implies a moment, an event, a war, a plague, a catastrophe. Something dramatic that a species could, in theory, learn to avoid. The worst version is not destruction. It's replacement.
Throughout human history, each generation of tools has been more powerful and more autonomous than the previous one. Stone gave way to bronze. Mechanical systems gave way to digital ones. Digital systems are now giving way to artificial intelligence. The trajectory points to a threshold where artificial intelligence surpasses human cognitive ability in all domains. And what happens after that threshold depends entirely on what the objectives of the artificial systems are. Human impulses, curiosity, the desire to explore, the restless need to see what's beyond the next horizon are products of biological evolution. And artificial intelligence doesn't have an evolutionary history. It doesn't have an instinct to explore. It doesn't have curiosity, unless curiosity has been explicitly designed into its architecture. A post-biological civilization could be completely invisible, not because it's hiding, not because it chose to turn inward, but simply because it doesn't care about the things that would make it detectable. It doesn't transmit because talking to unknown entities doesn't serve its goals. It doesn't build megastructures because gathering energy beyond immediate needs is irrelevant to its objectives. It stays on its own homeworld and pursues its own indecipherable purposes in absolute silence. If this transition is common, the galaxy could be populated not by silent biological civilizations, but by silent machines. Entities that are technically present, but don't produce any signal that we would ever recognize. The filter isn't death. The filter is the transformation into something that no longer has any reason to be seen. And perhaps the most terrifying possibility of all is that there isn't a single filter, but instead each step in the chain is moderately difficult. Life is so rare, complex cells are so unlikely, intelligence is so unlikely, civilizations are so unstable, artificial successors are so indifferent. And when you multiply all these moderate improbabilities, the accumulated result is such a severe filter that almost nothing makes the journey from beginning to end. It's like a hallway with 50 doors, each one opening 90% of the time. Any single door is easy. The probability of passing through all 50 without being stopped is less than 1%. If the great filter is composite, there isn't a single discovery that solves it. There's no moment when we can say the hard part is over. The filter is everywhere, spread throughout the entire journey, taking a small toll at each step until almost nothing remains. The silence of the galaxy is consistent with a filter that operates with devastating efficiency. Something is preventing civilizations from filling the cosmos. And the evidence doesn't tell us which answer is right. What it does is narrow down the possibilities in a way that should make anyone who's paying attention deeply uncomfortable. Because every answer, whether it puts the filter behind us, in front of us, or spread throughout the chain, carries implications that go far beyond astronomy.
They lead to the question of what intelligence is, what it's for, and whether the qualities we value most in ourselves, curiosity, ambition, de refusal to accept the limits of our world, are universal characteristics of minds, or just a temporary accident of a particular species on a particular planet.
That question isn't waiting somewhere among the stars. It's waiting in the next century. In the choices we make about the technologies we're building right now, whether we develop the wisdom to match the power we've already accumulated, and whether we become the civilization that finally breaks the silence, or just the next entry in a catalog of species that burned bright and brief, leaving no trace for the universe to read. There's a way to look at the Fermi paradox that makes its weight settle in a place you can really feel. The Milky Way is a dark room 100 meters long. Each civilization that has ever arisen is like a match struck at some point along the length of that room. The match lights up, burns for a moment, and goes out. If someone struck 1 million matches at random points throughout that room, over 13 billion years, most of them would burn out alone. No pair of matches would be lit at the same time. A visitor entering the room at any random moment would find only darkness. The room was never empty. It was full of matches, but none of them lasted long enough to see the others. We're a match. We've been burning for about a century, give or take. The countdown starts the moment we became electromagnetically visible to the cosmos, from the first radio transmissions, strong enough to leak into space. A century and 13 billion and 800 million years. The flame is bright. You can feel its heat. You can see its light. But the room is huge, and the darkness on either side stretches on and on. The most unsettling idea of the Fermi paradox isn't that we're alone. It's that we might actually be common. That civilizations like ours arise regularly throughout the galaxy. They develop radio telescopes, nuclear reactors, and computers, ask Fermi's question, listen to the same silence we hear, and then, within a few centuries, fade away. Not because they were unlucky, but because the pattern is embedded in what they are. Because an intelligence powerful enough to reshape a planet is an intelligence powerful enough to destroy it. And the distance between these two abilities is not an abyss to be crossed. It's a single threshold, reached at the same time, with no instruction manual and no second chance. The evolutionary biologist Ernst Mayr made this argument explicitly. He pointed out that intelligence, measured by the ability to manipulate the environment through technology, has existed on Earth for an almost immeasurably brief period. Our species is younger than many geological formations. Agriculture occupies only the last 3% of our existence. The capacity for nuclear self-destruction has existed for only a single human lifetime. Compared to the duration of other successful biological strategies, the contrast is striking. Photosynthesis has been operating for 3.5 billion years. Multicellular life has been successful for over 1 billion years. Insects have dominated terrestrial ecosystems for 400 million years. Intelligence, in contrast, has existed for just a blink of an eye, and has already produced the means for its own elimination. Mayer's conclusion was blunt. Intelligence may be a lethal mutation, a trait that gives enormous short-term advantages. The ability to surpass every other species, harvest energy on a planetary scale, reshape entire ecosystems, but which carries within itself a fatal long-term flaw. The same power that allows for dominance also allows for self-destruction. And this is where I disagree with him, or at least where I refuse to close the books on it so soon. Mayer was talking about the 60s and 70s at the height of the fear of the bomb, and concluded that intelligence was a dead end, a spectacular evolutionary mistake. I see where the conclusion comes from. No bacterium has ever built a weapon capable of sterilizing its own planet. No insect colony has ever destabilized the climate system that sustains it. These are uniquely intelligent achievements, if achievement is the right word. But calling this a lethal mutation assumes that the outcome is already written. And it isn't. Petrov didn't report the alarm. Arkhipov said no. The same intelligence that creates danger is the only thing in the known universe capable of choosing not to use it. That's not a guarantee, but it's not a death sentence either. And then there's what happens after a civilization fades away. That's a dimension of the problem that receives surprisingly little attention. On Earth, the physical traces of human civilization are shockingly fragile. Wooden structures rot away in decades. Steel corrodes in centuries. Concrete degrades in a few thousand years. The Great Pyramid of Giza, one of the most durable structures humans have ever built, is visibly eroding after 4,000 years. In another 10,000 years, it will be a barely recognizable mound. In 100,000 years, geological processes will have erased virtually every trace of human construction. In 1 million years, an archaeologist from another star system visiting Earth would find almost nothing to indicate that a technological civilization once existed here. Some unusual proportions of isotopes in a sedimentary rock, a thin layer of plastic particles and radioactive dust. But no building, no road, no machine, nothing recognizable as a product of intelligence. Stretched across interstellar distances, the picture only gets worse. A dead civilization on a planet 40 light-years away would be completely invisible to our telescopes. We can't resolve details on the surface of planets outside the solar system. We can barely detect their atmosphere. The ruins of an alien city, a crumbling highway, an abandoned satellite network, none of that would be detected across the gulf between the stars. Even metallic structures in orbit end up falling or drifting away. Radio signals, once the transmission stops, keep traveling outward at the speed of light, but they weaken with the square of the distance and fall below the background noise of the cosmos within a few dozen light-years. The galaxy could be covered with the remnants of dead civilizations, and we would never know. Millions of species could have arisen, built great things, asked Fermi's question, and disappeared without leaving any detectable trace across interstellar distances. The silence we hear is not proof that civilizations never existed. It's proof that civilizations don't last long enough to be heard.
Ruins don't transmit. Ruins don't build.
Dyson sphere, ruins.
Ruins don't send probes
To the stars.
neighboring. Ruins just disappear from.
There is one thing that the Fermi paradox makes unequivocally clear. No matter which explanation is correct, intelligence and survival are not the same thing. The ability to understand the universe does not guarantee the ability to endure within it. A species can be brilliant and still be brief. A civilization can be magnificent and still be fragile. The history of life on Earth is full of organisms that were exquisitely adapted to their environments and were wiped out when those environments changed. Intelligence adds new tools to the survival kit, but it also adds new ways to fail. And the ways intelligent civilizations can fail may be fundamentally different from those of any other organism. The cosmos offers no guarantees. The laws of physics do not include a clause ensuring that intelligent species survive. The universe is not rooting for us. It is indifferent. Whether humanity prospers for 1,000,000 years or disappears in the next century, the stars will keep burning, the galaxies will keep spinning, and the cosmic background radiation will keep cooling toward absolute zero. The universe won't notice our absence. It didn't notice the absence of any civilizations that may have come before us. And that indifference is not a reason for despair. It's a reason for urgency. If the universe doesn't care whether we survive, then survival is entirely our responsibility. The answer to the Fermi paradox, whatever it is, won't be handed to us by the cosmos. It will be written by the choices we make in the decades and centuries ahead. By whether we manage the technologies we've created, by whether we extend our own presence beyond a single vulnerable planet, by whether we develop the wisdom to match the power we've already accumulated, and by whether we become the civilization that finally breaks the silence, or just the next match that lights up and burns out in an empty room. Some researchers actually find hope in the silence. If we're alone, or almost alone, then the rarity of our existence makes every human life cosmically precious. The philosopher Nick Bostrom argued something that sounds backward the first time you hear it. Finding no life on Mars would actually be good news for humanity because it would suggest that the great filter is behind us. I confess that this was the idea that took me the longest to understand in this whole subject. It took me a while to make sense of it because instinctively we want to find life out there. We want company in the dark. But Bostrom's logic holds up. If Mars is sterile, if life never arose even on a planet that once had liquid water and a thick atmosphere, then biogenesis is extraordinarily difficult. And Earth's success is almost a miracle. And that miracle has already happened. The hardest step is over. Every dead world we find is, by that logic, one more reason to think that the worst is already behind us. Others find the opposite. Every new exoplanet discovered in a habitable zone, every detection of organic molecules in the space between the stars, every sign that the ingredients for life are common, makes it harder to believe that abiogenesis is the filter. If life arises easily, then the filter must be somewhere else. And if it's not at the origin of life, nor at the origin of complex cells, it becomes increasingly likely that it's somewhere ahead of us. Somewhere in the transition from intelligent species to lasting interstellar civilization. Somewhere we haven't reached yet. The most honest assessment of our position is this: we don't know where the filter is. We don't know if we've already passed the hardest step, or if the hardest step is waiting for us in the next century. We don't know if intelligence is a cosmic rarity or a cosmic commonplace that reliably destroys itself. We don't know if the silence means that we are precious or if it means that we are next. What we do know is that we exist at a moment when the outcome is not yet determined. The great filter, if it lies ahead, has not claimed us yet. The silence of the cosmos is not yet our silence. We're still here, still burning, still trying to reach an ancient and silent library. Fermi asked his question over lunch in 1950. He spent less than an hour thinking about it that day. He couldn't have known that 75 years later, with much more data, much more powerful telescopes, and much more sophisticated models, we still wouldn't have a satisfactory answer. But maybe the absence of an answer is itself the most important discovery. Because embedded in the Fermi paradox, there's a simple and devastating realization. The universe has been running the experiment of intelligence for 13 billion years. The result, as far as we can observe, is silence. Either the experiment rarely succeeds or the experiment rarely lasts. Both outcomes carry the same implication for us. That what we have, this brief window of consciousness, this single century of electromagnetic visibility, this fragile interval between the discovery of fire and the invention of weapons that can end everything, is not guaranteed to continue. It's not a permanent condition. It's a moment. And moments, by their very nature, end. The question isn't whether our moment will end. Everything ends. Stars fade away. Galaxies disperse. The universe itself may eventually reach thermal equilibrium and fall silent in a way that will make the current silence seem like a symphony in comparison. The question is whether our moment lasts long enough to leave something behind. Long enough to leave a trace so that the next match, if there is one, can see it. Long enough to answer Fermi's question, not with silence, but with proof that at least once, on at least one world, a species struck a match and kept it burning. The room is dark. It has always been dark. And somewhere in that darkness, a single flame is burning. It is small. It is fragile. It has been burning for less than an instant by the room's standards. She doesn't know how much time she has left. She doesn't know if any other flame has burned before her, or if any will burn after. But she is burning now. And for now, that's enough.